What's up, team? Today we are talking about isosceles triangles. Here's our learning target. It says I can apply theorems to solve problems with isosceles triangles. So that is what we are doing today. Here's what an isosceles triangle looks like. This is a generic isosceles triangle. We don't know all of the angle measures, and that's okay. But what we do know is this. If it is an isosceles triangle, then at least two of the side lengths are congruent to one another. So we have names for these parts of isosceles triangles. We don't know these lengths, we don't know these angle measures, but they all have names. So the two congruent side lengths of an isosceles triangle we call the legs. The third leg we call the base. Sometimes all three of the sides are the same. That's a very specific type of triangle. It's an equilateral triangle that we'll talk about later. But these two, the sides that are congruent to the legs, the other side is the base. The two angles that the base borders here that are adjacent to the base, we call the base angles. And the third angle we call the vertex angle. Let's dive right into a new theorem. Make sure to capture this in your notebooks. So the isosceles triangle theorem, it says, if a triangle is isosceles, then its two base angles are congruent. So this is a conditional statement. Hypothesis here is that the triangle is isosceles, and then the conclusion is that its two base angles are congruent. So what that looks like with our figure over here is that the two base angles here and here are congruent. So if you are given an isosceles triangle, you can determine two things real quick. The legs are going to have the exact same length, and the two base angles are going to be congruent to one another as well. So next we're going to dive into a couple examples. Okay, first example. It says the measure of the vertex angle of an isosceles triangle is 60 degrees. What are the measures of the base angles? We're not given any pictures, any figures, any other information. We know that the triangle is isosceles because that's given to us. So that's huge. That means we know that two legs are congruent to one another and the two base angles are congruent to one another. And we have the vertex angle. So if you're anything like me, this is hard to picture in your head. I need to draw a picture. So I can see it. So generic isosceles triangle. Don't know the angle measures yet. That's okay. I'm going to make these two my legs. I'm going to make these two my base angles. And now let's fill in what we know. We know that the vertex angle is 60 degrees. Looking at our other figure, the vertex angle is the one that does not touch the base. So that's this angle up here. We know in our case it is 60 degrees. And then these other two angles, we don't know what they are, but what we do know is that they are the exact same. They're going to have the exact same angle measure. So that's huge. That's really, really important here. So what we're going to do is we are going to create an equation involving these x's so we can solve here. Utilizing the triangle sum theorem that we studied previously, we know that 60 plus x must equal 180. When you add up all these angles together, they're going to have a sum of 180. So I'm going to do 60 plus x equals 180. We're going to solve this. We're going to isolate the x, and that's going to give us the other angle measures. So combining like terms, 60 plus 2x equals 180. Subtracting 60 from both sides, we learn that 2x equals 120. And then divide both sides by 2, and we learn that x equals 60. So this one's kind of weird. This is the one exception, or the one like really extra special case, I suppose, where we learn that x is 60. That means this angle is 60, this angle is 60, and we are given that this angle up here is 60 as well. So this is called an equilateral triangle where all three angles are equal and all three side lengths are equal to each other as well. If, say, we were given a different number, we can change this ever so slightly, and it'll give us a whole brand new problem. Say that the given angle here is 59 degrees instead of 60. It's so close, but it's still so different. So that means let's just reset up this entire equation and find our base angles. We're doing the second example just to show that all three angles are not always going to be the same. Following the same logic, we know that 59 plus x equals 180. 59 plus x equals 180. So we have 2x equals, I combine like terms. I'm also going to subtract the 59 from both sides to get 121 on the right-hand side. Divide both sides by 2, and we learn that x equals 60.5. So what this means is that the base angles both have a measure of 60.5 when the vertex angle is 59 degrees. Of course, you can be given any vertex angle here, anything less than 180 degrees, and you could follow the same process here to find the base angles. Now, what if you were given one of the base angles instead, and your task was to find the vertex angle? You do it the same way, just backwards, I guess. So say that we instead don't have what we just had. Erase this stuff. Forget about the stuff up here for a quick second. Say that we were given that this angle here was 40 degrees, and we don't know what the other base angle is, and we don't know what the vertex angle is either. Well, in isosceles triangle, base angles are always congruent, so we do indeed know the other base angle. So this one's actually a whole lot quicker. We know that these are going to add up to 180 degrees. We already have a 40 and a 40. That's 80. That means the vertex angle must be the difference between 80 and 180. So the vertex angle here is going to be 100 degrees. You could set up an equation to show that, but I think that one, it's not especially necessary. All right, got another example for you. This one, it just says solve for x, and we're given this figure. We have some algebraic expressions. It looks pretty yucky, but we'll be all right. We're just going to use the same ideas here. So here's what we know. We know that these two sides are congruent to one another. That means we have an isosceles triangle. So our vertex angle has a measure of 3x minus 1, and this base angle down here has a measure of 2x plus 3. Well, we know by the isosceles triangle theorem that we've discussed earlier in this video that the two base angles are going to be congruent. So this angle are the same. Cool. That means that the measure of this other base angle is also 2x plus 3 degrees. So the blue one was given, the red one we figured out based on that theorem. Now, another thing we know by the triangle sum theorem is that all three of these angle measures must add up to 180 degrees. So let's set up an equation that we can solve to get our x value, and that's all we need to do. We could then plug that x value in to find the angle measures. That's not what we're asked to do for this particular example, though. So here we go, 3x minus 1 plus 2x plus 3, and then just to show, we'll change the colors here, 2x plus 3, and when you add them all together, they have a sum of 180. Cool. I'm going to start by combining the like terms here. I have 3 x's, 2 more x's, and 2 more than that. 3 plus 2 is 5, plus 2 is 7. So 7 x's on the left-hand side. Now our constants, 3 plus 3 is 6. 6 minus 1 is 5. This equals 180. Subtract 5 from both sides. We learn that 7x is the same as 175. Dividing both sides by 7, I'm thinking of quarters like the coins here now. There's 7 quarters in $1.75, so x is 25. So that means we can plug in 25 everywhere you see an x in this triangle. The measure of this angle up here, 75 minus 1, so the measure of this angle is 76. Measure of this angle is 50 plus 3, 53, and this one must also be 53 degrees. Cool. We solved this triangle. The most important thing with this one is we had to recognize that it was isosceles. We recognized that because the two legs were congruent to one another, and then we used the fact that it's isosceles to show that the two base angles were also congruent, and then the triangle sum theorem wraps it up for us. Okay, one more example. This one's a bit of a doozy. I'm going to explain it a little bit, give you a super informal proof. We're not going to organize it as a 2-column proof, but we could if we wanted to. So here's the situation. We have a bigger triangle, PQR, a smaller triangle inside, TQR. We're given a few facts. PQ is congruent to PR, so PQ, PR, congruent sides. Cool. That means this thing must be isosceles. Awesome. Next, TQ and TR are congruent. So TQ, TR are congruent. Boom, boom. So that means the smaller thing must be isosceles as well, just by definition of isosceles triangles. Okay, Now our task is to explain why angle 1 and angle 2 are congruent to one another. So here's how I would start this one. I would say, I would start with the big triangle here, PQR. We know it's isosceles, so the two base angles must be congruent to one another. So let's mark that. We know that these two big base angles are congruent to one another. Now, let's zoom in on the smaller triangle, TQR. We know that both of its base angles are congruent to one another. So that's angles 3 and angle 4. This is going to look pretty funny here, but we are saying now that angle 3 and angle 4 are congruent to one another. We still don't know 1 and 2 yet, because this is the sum of angles 1 and 3. This is the sum of angles 2 and 4. So I think you see where this is going, but if we set up an equation here, we would say the measure of angle 1 plus the measure of angle 3 is congruent to, or equal to, in this case, because I have it set up this way, is equal to the measure of angle 2 plus the measure of angle 4. So it's basically angle R, the whole sum here, is the same as angle Q. Okay, now we can do a little bit of substitution because we know angle 3 and 4 are the same as one another. So I'm going to say the measure of angle 1 plus the measure of angle 3 equals the measure of angle 2. So I haven't changed anything yet. I'm going to do my substitution here now. I know that the measure of angle 4 and the measure of angle 3 are the exact same. So I'm going to plug in the measure of angle 3 right here. Now, we have the same term on both sides. I'm going to use the subtraction property of equality to determine that the measure of angle 1 equals the measure of angle 2, which is why angle 1 and angle 2 are congruent to one another. Okay, I know that one is a little crazy, a little bit weird, but there's all sorts of fun things that we can do with isosceles triangles and utilizing these different theorems. Okay, let's dive into the practice problems. Let me know if you have any questions.